So, hello, good morning everyone. My name is Krzysztof Opasiak. I work for Samsung R&D Institute Poland. I used to do a kind of USB related stuff in Tizen. I'm a libUSB-GX maintainer. Apart from this, I'm a PhD student at Warsaw University of Technology. My research is related to USB. To hacking using USB, to USB monitoring, etc. So what we are going to talk about today? We are going to talk about USB. Why USB, not Ethernet for hacking? Well, I think that USB is the most common external interface in the world. It is told that every year, 3 billion USB devices are being shipped to the market. So the scale is huge, and almost every smartphone has a USB connection. Every laptop has a USB connection. I would even say that even every nuclear power plant also has a USB connection, like the history shows. So what we are going to talk about today? First of all, I would like to give you some gentle introduction to the USB world, to the features we would then abuse in our attacks. Then we will focus on attacks which target USB hosts, so that the bigger devices like our laptops, PCs, etc. Then we will go through USB traffic analysis and maybe some modifications, and the USB device-related attacks. In the end, some short summary and Q&A session. So the first step, what USB is about? What's the goal of having USB in your pocket or in your laptop? This may be a tough question in the beginning. So let's think for a while what internet is about. Some of you may think porn, cats, and e-banking. I would agree, but I would generally call them services. So on a very general level, internet is about providing and using some service, like web page, email, etc. USB is about the same thing. It's about providing and using a service. Just this service is a little bit more low level, and the architecture of providing the service is different. In internet world, usually we use client-server architecture. In the USB, we've got enforced USB device, USB host architecture. So USB host is usually this bigger machine which is being used by the end user, like PC, like your laptop, not laptop, but your smartphone with OTG cable. The device which is held by the end user. And this device may lack of some features. Well, it's quite hard to imagine that you could print out something from the laptop. So that's why you need to connect your printer via USB. It's a kind printing in this way is a kind of service provided by the printer. Printer here is of course a USB device, while laptop is a USB host. So a single USB device may be connected only to one host. And a single host may have multiple USB devices connected in the same time. Single USB device may provide one or more functionalities in the same time. On a previous talk, Andrzej showed how to configure a USB gadget. As you saw there may be multiple functions inside one USB gadget. So those functions are directly functionalities provided by the device. Those functionalities may be totally unrelated to each other. So that's important then when we move further. So what USB device really is? What do you need to build your own USB device? First of all, you need some piece of hardware for USB communication. You need to have this electrical level. So you need some kind of equivalent of the network card. When you've got this, you need USB protocol implementation, because both sides has to speak a common language. When you can speak a common language, then you may say something useful. So to say something useful, you just implement some protocol on the higher level, like mass storage or human interface, etc. Then, if you're going to provide some functionality, probably you need some additional hardware or maybe some additional software to emulate that hardware, which could provide this functionality. For example, in your printer, you need all these mechanical parts. In your camera, you need the lens, you need the matrix, etc. So, this is what's needed. And what we get from the USB standard? We get endpoints. What are endpoints? In internet world, we could multiplex services on a single server using TCP or UDP ports. Endpoints are kind of equivalent of that port. The difference is that they are very limited. So instead of 65K ports, we've got only up to 31, but it depends on hardware capabilities. Each of them gets a unique endpoint address, and the main difference is that only endpoint 0 may transfer the data in both directions. What does it mean? It means that all other endpoints are unidirectional. So endpoint can be either in or out, not both in the same time. What are the consequences? Well, the consequences is that every USB device has to have endpoint 0. Endpoint 0 is mandatory and is bidirectional. So it means that in theory, every USB device, even if it doesn't have any out transfers, it can transfer the data from host to the device. I didn't tell you that the direction is always set from the host perspective. So in transfer means transferring data from device to the host, and out transfer means transferring the data from host to the device. And because endpoint 0 is bidirectional, it means that even keyboard that has only in endpoint for sending our keystrokes, in theory, if it is hacked, can exfiltrate the data using endpoint 0. It's not going to be fast, but it's also not going to be visible in network traffic. In internet world, generally we use two protocols, TCP and UDP, and we build something on the top of them. In USB world, we've got 4 types of protocols. We've got control 1, which is reserved for endpoint 0, which is mandatory and has specific format of request. We've got bulk, which is the most common. It guarantees the delivery, but doesn't guarantee the delay. Then we've got interrupt. Interrupt also guarantees the delivery, but doesn't guarantees the delay, but has a limited bandwidth, a very limited bandwidth, and it reserves it on the bus, so you cannot have too many interrupt devices on a bus. Then you've got ISO, and ISO is kind of mix of two previous because it's used to transfer a large amount of time-sensitive data, but without warranty of delivery. So just like UDP. You send and do not know if the data is right or no. So you use this for video streaming, audio streaming, etc. That's our only endpoints. And in internet world, this is when the story ends. You can just run nmap and see what ports are open on some particular server, but you don't know what those ports are used for. We've got a concept of well-known ports, so we always run some particular service on this port. But in USB, we've got only 31 endpoints. We are very, very limited. So we have to somehow say to what kind of service this endpoint is assigned. We use this grouping endpoints into interfaces. So interface is a group of endpoints that is used to implement some well-sandboxed functionality. And you shouldn't mix this with USB function from the previous presentation, because single USB function may use one or more interfaces. This is because in USB function, in some standards, you may need like 2 bidirectional channels or something like this. So the channel is the interface. Usually you will have two endpoints for functions like ADB or something like this, because this provides you a bidirectional link between host and the device. So interfaces are grouped into configurations. Configuration is a group of interfaces that can be used in the same time. Single USB device may have one or more configurations, but only one of them can be active in the same time. You can use only interfaces that are in currently active configuration. Endpoint 0 is kind of special. It's special because it's always available and it's not in any interface or configuration. It's used during the process of discovering this whole layout of a USB device. It's called enumeration. And enumeration is the main part of plug-and-play philosophy implementation. What does it mean? Plug-and-play means that you just connect and no one is going to ask you about anything. You may remember the old times when we used serial or parallel ports, and whenever you connect your modem, whenever you connect your printer, you have to go through manual and find what kind of settings you should use for this serial port. What's the speed, what's the parity check, etc. In USB, there is no such thing. Authors of the USB standard take care of all that stuff and introduce a process called enumeration that allows your USB host to discover the capabilities of USB device and then provide a suitable support for that device in your operating system. So, how is it going? First of all, you have to plug in the device. If something is not working, please always go back to that step and try to take it out and put it in once again. It fixes like maybe 40 to 50% of USB problems. Then you have to detect the connection, because when new device arrives, your USB host has to detect the connection. Then you need to set address for that device. Every USB device on a bus has its own unique address. This is 1 byte. So this is the obvious limit of maximum number of USB devices on a single bus, 127. Then when you've got address for some device, you need to get device information. Get device information means discover this layout from the previous slide. What's the logical layout? What this device offers to the host, and what kind of drivers should be chosen for it. Before we choose our drivers, we have to choose configuration. As I told you previously, we can use only interfaces that are in currently active configuration. So firstly, we choose configuration, and then we choose drivers for interfaces. It may be weird, because we used to say that this USB device doesn't have drivers in the kernel. No, it's not true. USB device, all USB devices share a single generic USB device driver. But the thing which provides you the functionality from the USB device, it's called USB driver, and it is bound to interface, not to whole USB device. Because single USB device may provide multiple unrelated functionalities, so there is no need to glue a couple of unrelated functionalities in a single driver. Just use drivers for interfaces. So how do we get our device information? We use structures defined in a USB standard called USB descriptors. Every entity from the USB world is described by a suitable USB descriptor. The first type is the USB device descriptor. It describes the USB device as a whole. What kind of interesting things we can find there? First of all, we've got the ID vendor and ID product pair. What it is? ID vendor is a 2-byte number which you can get from the USB organization. Obviously, it's not free. You have to pay for it. And what do you get for this couple of $100 you spend for those 2-byte number? Well, you get a guarantee that if your device provides some unique functionality and requires some unique driver, then you may use this ID vendor and ID product for matching with your driver. It also means that there is no need to change the ID product in newer version of your device if it is backward compatible from the USB perspective. So for example, most of Samsung Galaxy phones share the same ID product. So if you use old Ubuntu with all USB IDs database, and you connect your Galaxy S7 or S8, you will get the string Samsung Galaxy S2. Because all those phones are backward compatible from the USB perspective, so there is no need to change the ID product. Whenever you change the ID product, you're asking for troubles, because users of some older operating system won't be able to use that device easily. Then after the ID product, you get the B-device class, subclass, and protocol information. The same triple is repeated in USB interface descriptor. Why? Because if single device implements only one functionality, the information about class to which it belongs may be put in the device descriptor. If we have multiple unrelated functionalities, then we put this information in every interface. But what it means that device belongs to some class? It simply means that we declare that our device or our interface is implementing some well-known, well-defined standard. There is a couple of standards published on the USB organization website, and you may check that every standard says if you are compatible with this standard, you should set those values to this triple. What do we get from it? We get the ability to use the generic driver for that class. Thanks to this, inside your kernel, you will find only one universal driver for every pen drive in the world, because all pen drives declare that they implement the mass storage class. They follow the mass storage protocol, so we may use the generic driver, the same driver for many devices. What else we have? We've got also 3 strings, or to be more precise, 3 indexes of strings. Because apart from USB descriptors, we've got also strings. To get some string, you have to get its ID first. And this ID can be found in the descriptor. So this is just a digit, then you can pass it to another request and get the corresponding string in given language. The one Andrzej showed you that OX409, and then there was 3 strings, manufacturer, serial, and product. Those are indexes of that strings. Is there something that prevents you from creating a device which says that it has been manufactured by Samsung? No. There is no cryptography, there is no control, there is nothing that can prevent you from changing the information in those strings. Even for devices that are small, you can simply get strings on those binary, and you will easily find where those strings are and can change it. Different configuration may have different power consumptions, so we have the power constraints for configurations, the string in interface, and endpoint. In endpoint descriptor, you've got the endpoint address and attributes which simply told you what kind of protocol is used on that endpoint. So let's go further. If we know how to discover the capabilities of USB device, let's think why we need a driver for an interface. What this driver really is. First of all, usually a driver is a piece of kernel code. Not always, because we've got libUSB, so we've got a kind of user space drivers. But here I focus on the kernel code, kernel-side drivers. This driver usually provides something to the user space. Because if you connected some USB device which provides some additional functionality, additional capabilities, you would like to pass the ability to control it to the user space. So if you connected a network card, you should get a network interface into the user space. If you connect a serial port adapter, you should get a TTI to the user space. That's obvious. We provide some generic interface, and then what kernel driver really does is translating generic calls through that entity in the user space to calls specific to this USB device protocol. So it's nothing more than implementation of some communication protocol and matching it with kernel generic interface. So how to choose a suitable driver? First of all, we should know that we are focusing on something described using struct USB driver. And when device needs some special handling, we should use vendor ID, product ID, and interface ID. So if you're implementing some vendor-specific device, something which doesn't follow the standards, or you need some tweaks, some special handling, you should use vendor ID, product ID, and interface ID for that purpose. When driver implements some well-defined, well-standardized protocol, you should use the class information which I mentioned earlier. So how does it look on a big picture? We've got some USB device, and the USB bus, of course. We've got the hardware, which is USB host controller, the driver for that hardware, and the kernel representation of the USB device, which is struct USB device, with some generic driver, which is shared between multiple USB devices, and the only thing which it does is selecting a suitable configuration. And then you've got USB interfaces, the abstractions, drivers for those interfaces, and entities that they provided to the user space. What happens then? When we go from kernel to the user space, then what happens depends on your user space, and depends what you provided to that user space. If you provided a network device, then probably your network manager will configure it and you will try to use it. If you connect a pen drive or some USB disk, you will get a block device, so your automon service will catch this and try to mount it in suitable directory. If you connected mouse or a keyboard, your X11 will probably start to listen for input events using that input source. And many other things happen automatically in your system without any user action, since plugging in the device till starting using this by your user space daemons. And this is the stuff which we will try to exploit in USB host attacks. I think that the grandpa of all USB host attacks is Autorun. I think all of you know it. It's a really old and nasty attack when it was enough to put a text file on your pen drive to get some malware automatically executed whenever you connect a pen drive to the Windows machine. You may be laughing that it was a stupid mistake by Microsoft, but then I will tell you that Genome used to have the same functionality, just different format of that file. So what's the problem of Autorun? The problem is that you can easily craft some USB pen drive, connect it to some Windows host, and get your binary, which could be placed in the same pen drive, automatically executed. So what you are targeting here is high-level user space, which automatically executes some binary. It has been fixed So since Windows 7, Autorun is disabled for you by default for USB devices, and security patches for Windows, for previous versions of Windows, also disables the Autorun. So when Autorun stopped working, we needed something new. And this is the time when some agency, let's say it, required access to some nuclear power plants in Middle East. So that's why a Stuxnet has been created. What it is, we are still in very high-level user space. And what do? We use LNK vulnerability to get our malware once again automatically executed. What LNK vulnerability is? Some clever guy in Microsoft thought that every file should have a very nice icon. But how to do this? We could hard code, for example, some GIF images in file and point to that part of the file. Okay, it's good, it's nice. But how if we allow the developer to dynamically generate the icon? Yeah, seems like plan. So they implement it. And what turned it out? It turned out that you could create a file and set the icon property to any random binary placed on the pen drive. Whenever you try to list the directory which contains that file, Windows would try to generate the icon for it. And what it does, it simply runs this binary and waits for the result. Obviously, it never got the result, and the malware has infected the system. It was running over there with full system privileges. It may be funny, because it was back in 2010. And guess what? 5 years, obviously it has been fixed. A fix has been published, a long article on Microsoft web page. And then 5 years ago, not 5 years ago, but 5 years later, some security researcher look at this and say, oh man, you just fixed only part of it. It turned out that you could still run a binary, but using a little bit different version of this functionality. So that's why you should always pay attention to what you are fixing and ask yourself, are we fixing only the current attack, or are we fixing the bug that's really causing this vulnerability? And you should always fix the bug to prevent recall of that vulnerability. But what's the Stuxnet full history? This is the vulnerability. And the full history is that Stuxnet targeted Siemens PLC controllers. Those controllers were used in nuclear power plants to stir something, but there was a single problem. Power plant system was disconnected from the internet. So it was kind of hard to send malicious email, etc. to infect those computers. So they thought, USB sticks are getting cheaper and cheaper. Let's throw a couple of them on the parking before the power plant, and maybe some employee will pick it. And guess what? They pick it and connect it to their work computers, and it worked like a charm. You may be laughing that, okay, it was a couple years ago. People stopped doing such stupid things. Not really. Somehow around 2 years ago or something, a couple of researchers from America throw around 300 pen drives on a university campus. And guess what? More than 80% of those pen drives has been connected to computers. Obviously, the intention that has been declared by a person who found it was to find the owner. But if there were two directories, private data, where it could be used to find the owner, and private photos, guess which one was open first? So, people are still connecting any random USB devices found on a street. If you connect your home keys to that device and throw it on a parking, there is almost 100% chance that people will mobilize itself and connect it to the computer to find the owner, because there are home keys. It's very important to find the owner and return the keys. So what can we do next? This is high-level attack. We are still targeting the very high-level software. But this can be fixed. So let's try to get to the lower layers. We could attack the USB protocol implementation itself. Why? Because implementing protocols is not an easy task. You can make many mistakes in parsing, for example, descriptors. You can make many state-related mistakes. You can make buffer overflows. So there is a lot of places where you can make a mistake. And the problem is that many devices that are USB hosts are not running Linux. Because Linux is thought to be relatively safe from that attacks. But many embedded devices are not. So what kind of attacks we've got, we know from the history. The first one presented on the Black Hat conference around 10 years ago was called plug and root. It was a crafted USB device that, when a host asked for the descriptors, sent more data than expected. It turned out that the buffer to which the data was received was on the stack. And guess what we can do? We've got the classical buffer overflow and return-oriented programming, and we are, let's face it, we've got kernel code execution, and nothing can protect us. The next one is the PS Group. PS Group, who had PlayStation 3? Anyone? No PlayStation players? Lucky you. You always played computer games on Linux. Okay, so the problem with PlayStation 3 was that Sony decided to block unauthorized games from being run on the console. So some clever people said, okay, so how can we jailbreak the console and get the full rights and run those unauthorized games? It turned out that there is a vulnerability in Sony implementation of the USB protocol. When host enumerates a new device, it asks for configuration descriptor in 2 steps. Because configuration descriptor may have different length, so you need to know how big should be the buffer to be allocated for this descriptor. So in the beginning, you ask for first 8 bytes of configuration descriptor. 8 bytes because this is where you will get the descriptor length. Then you allocate the buffer, and then typically you allocate the buffer and ask for the descriptor once again with full length. The problem was that obviously the request to the USB device was formed that PS3 was asking for the first 8 bytes. But the device can respond with any random amount of data it has. And guess what? On the side of the PS3, the buffer was indeed 8 bytes, but their hardware didn't check the real amount of data sent by the device, because hardware could stop the transaction and say, okay, 8 bytes is all I need, I don't want more data, and just knock it. But they did not do it. They simply received all the data sent by the device. And guess where? Yes, to the stack. Currently, those kind of attacks are hard to achieve, especially on Linux, but they are quite possible on some embedded devices. For example, you can get some such attacks on some cars, on some DVD players, on many different devices that doesn't run Linux. I don't know why. Okay, so what do we use to track such mistakes? We've got something called USB fuzzers. Those fuzzers, from the hardware perspective, are something like Face Dancer. Face Dancer is a simple device that can be connected to two hosts in the same time. One host drives this simple device, and the second one receives some random calls from some random USB calls or some random USB re-enumerations to the USB device. There is a version of those fuzzers which use GadgetFS, which is a Linux interface, and FunctionFS. What this gives you is the ability to drop the Face Dancer, and you can run part of those fuzzing on some single board computers which have UDC, like Odroid, which Andrzej used during his presentation, or maybe BeagleBowl. From the software perspective, we've got mostly UMAP and UMAP2. Some time ago, even on the Linux USB mailing list, there was a guy who ran UMAP on a Linux stack and found a couple of mistakes. So in security, there is no such thing that you run it once and say, okay, I'm not vulnerable, I'm safe now and forever. No, your software is evolving. Linux kernel, and the USB protocol, implementation in Linux kernel, changes from every release to another release. So this is a constant process, and you should run those fuzzers every time you get your software, you are rebasing your patches, you are releasing your product. So now it's time for another attack. Let's go with my tablet. Is it a tablet? Does it look like a tablet? Does it look like it's running Android? Yeah. So if someone comes to your office and say, come on man, my battery is almost empty and I have to send a very important email. Could you please charge this for me from your computer? Would you say yes? No? I guarantee you that many people would say yes. And guess what happens? Let's go to some different screen. Connected to the computer. We do not expect such a tablet to do any harmful thing for our computer. We also do not expect such a tablet to open a terminal. It's kind of unexpected, yeah? And probably we do not expect such a tablet to change a desktop background. So what happened here? First of all, I connected some hacked device. I used the tablet, but the original version of this attack was using pen drives. Why pen drives? And how? It turned out that most of USB devices on the market are being shipped with firmware upgrade unlocked. And this firmware can be upgraded using the same USB interface that is used to provide the functionality of that device. So you can connect the device and craft some special packet and send it to that device and say, now switch to firmware upgrade mode. And then you can just put a new firmware on that device and change the behavior. It turns out that the USB chip inside, for example, most of the pen drives is universal. It's some standard microcontroller that you may use to implement any random USB protocol. By default, it's mass storage and communication with the flash memory. But you can use this to implement, for example, human interface, like I did here, and send some random keystrokes to the host to which you are connected. How do we protect against it? Well, we can protect against it using, for example, USB Device Authorization. It's a feature that prevents any driver, any user space application from communicating with the USB device until user explicitly authorizes this device to use. So now let's go further. Let's go to USB traffic analysis and modification. Is it something new? No. It has been known in PS2 times. It has been popular, especially in public libraries. Do you remember times of internet cafes? You remember it, yeah? You went there and spent long nights over there, yeah, I know. So that's usually where those kind of things you found. You could find. What is it? It's a simple passive man-in-the-middle attack, and you just log every keystroke that goes through the device. What it gives you? Well, after a week, you probably have most of passwords from your school or from your hometown, etc. This attack has been a little bit more developed in something called BadUSB 2.0. What BadUSB 2.0 introduced is active man-in-the-middle attack. Because in passive one, you could just get passwords from the USB traffic. In this one, you can start playing with the user. How? For example, when you discover that your user is trying to put money from one account to another and is using one-time password received from the bank. So you may put the device which has a constant internet connection with the hacker, obviously, and when user logs into the bank, we already know that we may get his password and login and password there. So we are sending this to hacker, and hacker creates another session, login. So user starts creating a new account transfer. Hacker does the same, but with different target account. When user gets the one-time password, hacker. Okay, I didn't told one thing. That kind of attack can not only use human interface, but can also introduce itself as a network card and craft the system to get all the network traffic from the host. When you get all the network traffic, you can put the money in the middle, and instead of getting only human interface keystrokes, you can also play with the internet traffic and create another transfer. When user receives the one-time password, you just simply change one digit when he's writing it. He gets incorrect code information from the bank, and hacker used this one-time password to authorize his own money transfer. I think okay, this wasn't good. Let's go further. There is a generic framework for doing things like BadUSB 2.0. It's called USB proxy. It uses libUSB and GadgetFS. Currently, it works only on BeagleBone Black, but it should work on any board, but there are some kernel patches needed for GadgetFS. So currently, it's only for BeagleBone Black. I use it to play with ADB. I make it working, but it needs some love, a lot of it. Really, it's quite hard piece of code. It's very useful. It allows you to intercept with any protocol you want. You just write a dissector, and you can do anything. You can use it to modify the traffic to fuzzy for fuzzing, etc. But it is hard to fix if something is not working. Okay, that was host. We've got the traffic. And now let's try to attack our device. So our devices are getting more and more powerful. It's very nice because all the games works smoothly, etc. But this creates some problem. The problem is called power consumption. So you have to charge your tablet, you have to charge your smartphone. And guess what? Usually you have to charge it on the airport, you have to charge it in shopping mall, etc. So those are examples of charging stations from Poland. This is the one from the bank which you can connect your computer to some random USB port and just do e-banking and stuff. That one looks really strong. It's made from metal, but it even doesn't try to hide that it has a computer inside. When you connect your phone, it can even show you, okay, you connected to your phone, I see it, nice, Galaxy S7, And the last one is just from the bus stop. And guess what this charging station can do? On the left side, you've got the information, you've got the phone screen from Android 2.3.6. How does it look like when you connect to the charger? So here we are only charging your phone. And when your phone discovers that it has been connected to the computer, it asks you if it should provide some private data to the host. That was in Android 2.3.6. So whenever you are connected to the computer, instead of a standard charger, you see a big black screen. Looks like dangerously, yeah? But guess what? We are evolving. We are moving to new versions of Android. We are more user-friendly. So we don't like big black screens. So whenever you connect your phone to charging in Android 4.4.2, you've got this screen. And when you connect to the computer, you've got only a small USB icon on the top and a short connected as a multimedia device for a short period of time. But guess what? We are evolving. And instead of not only automatically providing user data to the host, we are also hiding a USB connected message in Android 5.1. So on the left side, you've got the screen when you connect to the USB charger. On the right side, you've got the screen when you connect to the USB computer. This is the place when any random host could access your private data. The only difference is when you swipe your finger to the notification screen. Fortunately, Google likes to create conferences and say, here's success. Come on, man, we make your life more secure. So, after when they screwed up from Android 2.3 to Android 4.4, they now created a pop-up screen like it was a couple years ago and say it's a huge success because we finally make your phone secure. Okay, the last one is ADB resource exhaustion. It's a bug in old ADB implementation, and only the root cause is the most important here. It allowed to get a root access to any Android phone because someone forgot to check the return value from set UID. That's all from me. Remember that USB is everywhere and that USB attacks are evolving, and because probably you are not going to face it unless you are an important person and someone will have targeted attack against you. But you don't know if there is some kind of person who would like to target his attack against you. You never know this. You never know how important it can be for someone else. Thank you. Do we have some time for questions? Okay.
How did you craft your tablets to act as a keyboard?
How I did it? Well, I used config.fs. I recompiled the kernel because here we've got 3.10, so it's pretty old. I put up around 100 of USB patches from kind of Tizen kernel. So I backported it to Android, and then I got the whole USB config.fs stuff up and running, and then I simply used libusbgx to configure the gadget and use the human interface function to send the keystrokes. What's a benefit, I may tell you, that newer version of Android, for example, if you take some new Android phones, use ADB which use functionFS backend. And functionFS allows you to implement any random function in the user space without the need to change the kernel and without the need to recompile it. So only with rooting the device, you can do some nasty stuff. I think this is enough to say.
Have you published the backported patches for 3.10?
No, I did not. But I may do this if you like. Just write me an email to. I'm not going to remember about it. And I say it's very dirty. It was like a mess.
As I remember, when you connect the phone for the first time to computer, it still asks for action.
Yeah.
It doesn't show up. For example, when I connect smartphone, it shows up like a device like this. In my case, it's Xiaomi, yeah. But unless
you mean that kind of screen, or
on a computer side, on the host side,
it asks for.
It shows like a device, but it doesn't act. Doesn't do some automatic actions.
I don't know. It looks like you have some problem on the host side. It's.
For example, Ubuntu. I also used Ubuntu. I didn't. We need to check your devices other computers.
Okay, so if I understand correctly, you mean that you connect your phone, you allow for communication, but you cannot use it from the laptop.
No, I mentioned that unless you allow something from the host side, it doesn't.
No. Generally, I don't think that there is any kind of authorization from the host side. What is and what was embedded even in that version of Android was that USB communication is not working unless the screen is unlocked. But you need to have the pattern lock or pin lock. If you have it and screen is locked, there is no USB communication. But when you only unlock it once and then lock it once again, USB communication is possible as long as you don't disconnect your phone from the computer. And what Android 6.0 did, they just added this pop-up. So now every time when you connect the computer, and even if you don't have the lock pattern or the pin lock, you will get this pop-up, and every time you will need to authorize some USB host to access your data of your device. So this is the change. It was possible in some vendor modifications of previous version. I know that LG did this for their phone, that you could choose your USB profile, charging only, MTP, ADB, etc. But it was vendor specific. And now this is embedded in mainline Android. Okay.
I could comment previous question a little bit. I think Guy mentioned when you connect device to Ubuntu, we don't see any notification about what kind of device did you connect. But for clarification, if you go into LS USB utility, you can see there USB hit device standard header, and then some kind of script execution. It's just a technique.
This is what I told you, what I mean when I was talking about the USB device authorization. It's a feature that you can disallow any new devices to the host, and every time when you connect a new device, it will get enumerated, but configuration for it won't be chosen. So you've got the time to use LS USB, to use dmessage, to check what kind of USB devices you have really connected. If you connected a tablet and you open your dmessage and see keyboard, then probably something is wrong, but it's up to you to decide whether you authorize it or not. Okay. I think we are out of time.
Just one question is fine.
Okay. Do we have some more questions? Yeah, Rosa.
So, any recommendation for end users? How to...
The recommendation for end user is that if you find any USB device on the street, then please don't connect it to your USB to your computer. If you really need to connect it, then first of all, make sure that you are running pretty recent kernel. Make sure that you are using USB device authorization. Now, those are two simple things which really increase your security, which gives you time and ability to control what kind of traffic goes to your USB host. If you are using a car, or if you have some DVD player that runs some embedded systems, then you may buy some face dancer or get some BeagleBone Black, etc., and try to fuzz it. You may get some unexpected results. And report it to the manufacturer. That's all I can say. Thank you.